Solid-state lighting, such as the LED light bulb, has been replacing traditional incandescent and fluorescent light due to advantages such as high efficiency, long lifespans, and environmentally benign components. The phosphor, more specifically inorganic phosphor, is one of the most important components in solid-state lighting devices. For example, we can coat phosphors on a LED chip to achieve white light emission. The discovery of inorganic phosphors has mainly relied on the trial and error method, which is usually a slow process. However, machine learning methods enable the fast screening of potential phosphors, which can largely accelerate the discovery process. For example, phosphor host has to be an insulator with moderate bandgap energy. Therefore, machine learning algorithms were used to build models to predict the bandgap of all inorganic compounds compiled in databases. The prediction happened in two stages. Firstly, I built a classification model to categorize metals and nonmetals. The bandgap values were then predicted for those nonmetals with a regression model. My models were based on experimentally measured bandgaps rather than DFT calculated values. The comparison between the model predictions and the DFT calculated values indicates the prediction is closer to experimental values than DFT. With these models, we can narrow down the screening space to insulators with a suitable bandgap. Moreover, we can combine bandgap energy with the Debye temperature model to construct a sorting diagram. Debye temperature was proven to be related to the phosphor efficiency. A high Debye indicates a higher chance to obtain a highly efficient phosphor. Besides, the sorting diagram can also be visualized based on compositional categories. Compounds with proper bandgap and high Debye temperature were selected to be carried out in the lab. With this screening method, we discovered a blue-emitting phosphor with efficiency as high as 95%. Besides proper bandgap and high efficiency, a good phosphor should be thermally robust. Thermal quenching temperature T50 is used as an indicator of thermal behavior, which is the temperature when the emission intensity is half of the room temperature value. A machine learning regression model was developed based on experimentally measured T50 data. The T50 for more than 1,000 potential phosphors were subsequently predicted. The experimental validation results demonstrate the reasonable prediction power of the machine learning model.